right now.
Hello.
All right. Good morning, everybody. It is 10:20, so we're going to get started. Everyone should have been muted by now. So I'm going to share my screen. And we're going to share. There we go. Let's see. There you go. So we are going to share. Okay, so everybody should be able to see my screen right now. Great. All righty. Okay, so I just want to get started today with a few notes. Some of you have reached out and asked about the pass, no pass option that you received an email about from the provost. One of the things I should mention is that this is not official yet. As per the language of the email, the motions have to pass the University Senate for it to be approved. So we realize, this is an anxious time and there are some, still some uncertainties. So, but from, the professor point of view, we'll work with you if that passes, if that's something you, want to pursue after you've consulted with your undergraduate advisor. And of course, your undergraduate advisors right now have the same information as you do because the proposal has not passed the University Senate yet. So that's still unofficial. And one of the things I just want to mention, in some of the questions that have come up is, admissions to your major will still be dependent on letter grade. So if this course is considered to be counted in that way for your major, then of course that's something you have to keep in mind, and it may not apply to you, but there might be a small subset in which that applies to. Okay. So just something to keep in mind. Okay. So before we go on and talk about the remaining concepts in thermal conductivity, I just want to review a little bit about our discussion on heat capacity at constant pressure and constant volume. And I've jotted down some topics here so that I'm sure to get to them. So when we talk about heat capacity for solids, really they can be used sort of interchangeably, because if you can imagine, at standard pressure and temperature, if we're on Earth here, the CP and CV don't change too much. The molar heat capacities don't really change. Now, when you normalize by when you talk about specific heats, that might change, obviously, because that changes based on the amount of material that you have, right, based on its molar mass. But when we're talking about just CP and CV, the big CP and big CV, the molar heat capacities, we're really just talking about that they're quite the same. They're very similar for solid material. So some of the examples that you've seen have either CP or CV, and I've used both of them. There's a little bit of some background noise due to some sirens that are outside right now, so bear with me. One of the other things I wanted to clarify before we go on is the concept of the Debye temperature. We talked about how CV can be calculated and modeled as a function of temperature with these types of curves that you see here. So the black, blue, and red curves. So what you see, what we talked about before was, CV as a function of temperature. And we had this regime where, asymptotically it goes to 3 times the gas constant. And in this region here, well, heat capacity goes to 0 because at 0 Kelvin, right, there's no heat capacity. And then in this regime here, it scales as A, which is a constant, times T cubed. Okay. So this is an example for one material. What happens when you have another material? So let me pick a different color. You could have some, well, actually so you could have something, that also scales as T cubed, and then it rises, but at a different rate, and then asymptotically reaches 3R. You could also have another material where maybe it rises a little bit faster, but asymptotically, it also goes to 3R. And so, we can normalize and where, and they each have their own Debye temperature, these different types of materials. And so we can normalize all of these different rises if we divide the temperature by each of the materials' Debye temperature. And then we get this universal scaling regime where we can map all of them on there. So here, close to 0 Kelvin, you get the T cube due to vibrations, and then they all reach 3R at some point. Okay, so I hope this clarifies some points on the concept of what a Debye temperature is and where that temperature would transition, for the heat capacity. Okay, so let's go all the way back. So let's see. So now, if there's no questions right now, we'll continue on and pick up where we left off. Yes, so if you scroll forward in your notes, the question in the chat, are we still doing top hat? Yes, so if you fast forward on the notes a little bit, you'll see that there is a top hat question. Okay, so where we left off last time was talking about the interatomic distances of different types of materials and how, due to the asymmetry of the bond energy curve, the interatomic distances increase, as you can see here. So that's what we were talking about last time. And if you don't have symmetry, then of course you wouldn't expect changes in the bond length. So the asymmetric curve, as you increase temperature, you'll increase interatomic separation, and you'll have thermal expansion. For symmetric curves, which is more representative of an ideal case, a model, a spring model, or ceramic type materials, as you increase the temperature, you'll not see an increase in the interatomic separation, and thus there won't be any thermal expansion. And as you see here, ceramics generally have lower coefficient of thermal expansion because they tend to have more symmetric bond wells, whereas in contrast, polymers have high coefficient of thermal expansion, and that's all due to the weak secondary bonding that exists in the van der Waals layers between the polymeric chains. Right, so polymers more asymmetric, ceramics less asymmetric, or more symmetric, less asymmetric. So that's where we left off. And here I've just highlighted the points so that we have a better understanding of thermal properties of materials at either end, so ceramics and polymers. So speaking of top hat, I'm going to issue the top hat now. The question is, A and B are different materials. Which material has a larger coefficient of thermal expansion? All right, so let me pull up top hat. Okay. So you should see the question on top hat now. Okay, so some of you have answered. $79. Okay, we have one more person and then we can move on. Okay, so let's see. So all of you have answered, so let me pull up top hat so you can see that. Okay, so let's see. So now I'm going to look at the responses. And so 67, yeah, so 67% of you have said that, let's see, let me share the screen. Screen share. So 67 of you, 67 answered A, and 16 answered B. And the correct answer is, oh, I see. I think I may have marked the answer wrong. So the more, sorry. Let's go back to the PowerPoint. Okay. So here we can see that what we're really looking for is the asymmetry, right? So if something is more asymmetric, then it should have larger thermal expansion. So that's what we're looking for. We're looking for more asymmetry, and thus A would have higher, would have more asymmetry. And so perhaps it looks like that my drawing doesn't make this, this B curve more symmetric. So I think that's probably why people logged in the answers that they did. So it would be A, since A should be more symmetric. So if we drew a cartoon, it would look more like this, where let's say this is 0, this is R going into infinity. If you have, that would be more asymmetric, and this would be more symmetric. So we would assume that this curve has a higher linear coefficient of thermal expansion. Okay, so that will have to be fixed on top hat. Okay, so the next part, I wanted to continue with an example of INVAR. So INVAR is a 64 weight percent, has 64 weight percent iron, 36 weight percent nickel. And the length of this ferromagnetic material is that it's virtually invariable as a function of temperature. So you can imagine that if you're looking for, if you're looking for a material, or you're designing a material that's stable and doesn't change, doesn't lengthen too much, or doesn't change volume too much as a function of temperature, you can imagine, that's useful for a number of sensor applications, devices like that. And here, INVAR can be used in examples where you want stability over time and also temperature. And so that would be a watch. What's interesting is that if you just look at, we just talked about bond energy curves, right? So if you just look at the potential energy curve, it's actually not explained in full. And so here, once again, we have to we're foreshadowing the magnetism module, but clearly, the properties of a material, it's sort of all convoluted, especially if there's magnetism involved or if the material is magnetic in some way. So here you see that 64 weight percent iron, and as you've seen with the iron wire demo, at very high temperatures, you could see that the iron wire went through a magnetic transition where the magnet fell off of the wire, and so as you increase temperature, what we've discussed so far is that there's a lengthening mechanism, right? There's an expansion of some sort. And that goes for most materials. Of course, there are some materials that actually have negative coefficient of thermal expansion. And what that really means is that the material contracts, right? It's not that it's negatively expanding, it's contracting. In this particular case, though, the material is expanding with temperature, but there's an opposing force in which you'll experience some contraction, and that's due to magnetorestriction. So that means the spins within this material for iron is that they're correlated, and thus there's the magnetism is actually constricting the expansion. So they're dueling forces. And so while you experience expansion as a function of temperature, there's a opposing contracting force. And so it makes actually this material invariable in terms of the size as a function of temperature. And so, that's been used in watches for precision movement, but more recently it's been replaced by, this beryllium, copper, iron compound, but of course, alloy for higher precision. But one thing we should note, when you're thinking about material selection and materials design, while you do have higher precision for by going to this beryllium copper iron alloy, you do have to consider that beryllium is actually highly carcinogenic. Handling beryllium on its own isn't necessarily terrible if you have proper protective equipment or PPE, personal protective equipment, but when the beryllium cracks, that's when it will release fine mists of beryllium and beryllium oxide, and that's when it can become quite dangerous to work with these types of materials. So it's highly carcinogenic. So something to keep in mind as we discuss materials engineering and considering all of these materials. Okay, and so here I highlighted, the thermal expansion for INVAR, as you see here. Let me change the color. So shows up a little bit better. Yep. For invar and super invar, which is a different composition of iron, nickel, and now cobalt as a ternary component in the alloy. You could see that the linear coefficient for thermal expansion is quite low relative to, just traditional aluminum and copper. So those are the values that you see here. Okay, so then when we put two materials typed together, we could ask ourselves, well, how would that material behave when it's coupled with another material? So, one of the examples is, if you have a brass lid on a glass canning jar, you have brass next to glass. So then if you consider that your glass jar, let's say it's borosilicate or Pyrex would be the commercial name, that has a linear coefficient of thermal expansion of 3.3, and then brass here is 20 ppm or parts per million, or in this case, we write it out as that. And sometimes you'll see it as micros as well, because that's 10 to the minus 6. Okay, and so what we have to think about is then, how does the material behave? So will your glass canning jar loosen? And it will, because brass has greater coefficient of thermal expansion than glass. Okay, so it will actually expand against the glass, and it will actually loosen as you increase temperature. Okay, so let's go over an example where we can see a material go through a wide range of temperature for thermal expansion. So here, let's say you have a rectangular aluminum casing that has the following dimensions, 25 by 3 centimeters, and this is at 25 degrees Celsius. So here, this is 25 centimeters, this is 25 centimeters, and the thickness is 3 centimeters. So what is the width of the mold? So here you're going to put this casing into, you're trying to make this material, and you need to make a mold. So if you're going from 25 degrees C to now, let's say you're going to a higher temperature, 655 degrees C, and the melting temperature for aluminum is 660 degrees C. Okay, so you haven't melted the material just yet at 665. So here you're given two values for the linear coefficient of thermal expansion. One is 23.2 times 10 to the minus 6 per degree Celsius at 25 degrees C. And the other value is 33.8 times 10 to the minus 6 per degree Celsius at 655 C. And so first, we need to know the relationship between the fractional expansion, so that's delta L over L naught, and the temperature range to eventually know how to get to the number or the width of the mold, right? So we know that this material is going to expand somehow. So what's the relationship between the temperature change and the linear and the fractional change? And so we know the final length. And so if we assume this is cubic, which it is because aluminum is FCC. So we know that the fractional change, LF minus L naught being the starting value, is related to the linear coefficient of thermal expansion times the difference between the final temperature and the initial temperature. And here, since we're given two values for the linear coefficient of thermal expansion, 23.2 ppm and 33.8 ppm, we can actually take the average, because what you'll often see, when people report, here's temperature, when people report the fractional change, sometimes you can go through the values for alpha naught can change a little bit. So, do you take the average? Do you take some instantaneous value? Sometimes it's reported as one or the other. So here we can see that we're given two values at two different temperatures. And so so we can actually just take the average of the two as opposed to taking an instantaneous value at any given temperature. So if we do that, then we can just take the average, right? Which will give us a value of 28.5 times 10 to the negative 6. Oops. Per degree Celsius. And then we can use this average to measure the final length, which is the width of the mold that needs to be made to accommodate this thermal expansion. And so LF is just L naught plus L naught times the linear coefficient of thermal expansion times the difference in the temperature. So basically I just rearrange this equation. And so we get 25 centimeters plus 25 centimeters times so you could see that, we need quite a much larger mold, 25.4 centimeters to accommodate this original casing of 25 by 25 by 3 centimeters. So let me pause here for a little bit because I've noticed quite a number of questions that have popped up. So Janet has been moderating. So Janet, I'm just gonna, and Tony as well. So I'm just gonna go back and take a look quickly to address any questions that haven't been answered yet. So Tony and Janet, can you unmute and just highlight for me the aggregated questions that haven't been answered? The question is there a way to mute the chat? Yeah, the chat has, yeah, you can just close it.
Sorry, you wanted us to unmute. Oh, no, that's not working.
Yeah, if you can just unmute yourself and just give me the highlight, because the chat question list is kind of long and it'll take me a little bit of time to go through it. So if you can just highlight for me any unanswered questions or something to highlight.
Okay. So there's a question here about the relationship between heat capacity and coefficient of thermal expansion.
Mm-hmm.
They're just curious what that relationship is.
Mm-hmm.
And let's see. Oh, come on, computer. A relationship to the thermal expansion and the change in volume, whether or not that's related to cooling rate. And
okay. Yeah.
Let's see, what else do we have? Why are we, I guess the question here is, why are we doing volumetric expand, or why are we doing just the change in L when we have a volume, or when we have the volume of the aluminum?
Okay, so I'll pause you there just because I'm starting to forget the questions already. Yeah, so let's tackle 3 at a time.
Yeah,
but thank you, Janet. Yeah, so the first one was, why are we doing linear expansion? Well, so here it's asking about the width, right? So we assume that the depth of this mold is not an issue. Aluminum is also FCC, so it's going to expand in a cubic manner. And so previously, when we were talking about when can we use the approximation that, the volumetric expansion for the the volumetric coefficient of thermal expansion, when can we use that? We can use that when we can assume that a material is going to expand isotropically. So for cubic materials, that's going to be the case, right? Of course, some of the examples I gave last time was that if your material has some anisotropy in the crystal structure, like something is tetragonal, right? So A is equal to B, lattice parameter, but not equal to C, or maybe something's hexagonal, right? So you have in the basal plane, A is equal to B, but not equal to C, or orthorhombic, where A is not equal to B, is not equal to C. So for those cases, one would expect anisotropy, and one couldn't assume that there's going to be the same rate of expansion in each of the crystallographic directions, and thus there would be anisotropy. So you couldn't assume that. Now you can approximate it, sure. Generally speaking, you can try to approximate it, but of course, if your crystal structure is asymmetric, then you would have to deal with anisotropy. This is a simpler example where we're just calculating, the expansion in one dimension, and thus I'm dealing with just the linear coefficient of thermal expansion. Of course, one could always change this and calculate the changes in volume. The equation is analogous, where you have changes in the volume, so the fractional change, and thus you would have to know what the volumetric coefficient of thermal expansion would be. So what was the second to last one, Janet?
Let's find it back. So there's a decrease. So does the coefficient of thermal expansion, or does the change in the total volume, is it affected by cooling rate?
Yeah, it is. And so there we'll talk about thermal shock and thermal stresses. Yes, if you quench very quickly, the surfaces of your material will experience a different type of expansion or compression based on the rapid change in temperature. So yes, and we'll get to that in a little bit. And sometimes you can use that to your advantage, actually. If you've ever seen glass being quenched very fast, the outside you can introduce some compressive stresses that will actually strengthen the material. And so, yes, absolutely. So we'll talk about thermal stresses and thermal shock.
So I guess just to clarify, does the total volume change that occur, is that affected by cooling rate, or is it just the rate at which the volume changes?
The rate at which the volume changes. You mean, oh, I see. So the change in this, or well, that depends on your material, right?
Mm-hmm.
I mean, at some point, if you have a bulk type material, you're going to have some limited penetration depth, right? Where the bulk of your material is not experiencing what your surface is experiencing. So dV in that case, and even rate of change in dV, dV dt, T being time, not temperature, right? I mean, that's going to change based on your quench rate,
Mm-hmm.
And that goes back to your TTT diagram.
Okay.
So for these cases, we're going to, apply, a simplistic model where we say, okay, dV dt, as in changes in volume over change time. So that's your change in volume rate. It's basically going to be very similar, right? So.
And then we had a question saying, hold on, there's more questions.
Okay.
Sorry. So is there a relationship between heat capacity and coefficient of thermal expansion?
Yeah, and it depends on if you're talking then about isochoric or isobaric conditions. So isochoric being, that dV is 0, isobaric is, when your dP is 0, so your constant pressure or constant volume. It can, if you're looking at the statistical mechanical model where you're taking into account translation, rotation, and vibration, right? So what I mean by that is your CV and your CP can. So, okay, let's find a new page. Let's actually go back. Let's see. Let me see if I can find. Yeah, so here you have your potential energy as a function of interatomic distance. Let me see if I can go back to. The short answer is potentially yes, right? Because it depends on what temperature your system is at, and then you have to consider that the energy of your system as a function of temperature at either constant volume or constant pressure. This is going back to statistical mechanics. Certainly could be, right? Because that. Excuse me. Hold on. Okay. Right, this has built into it all the rotation, vibration, and electronic translation of the atoms built into it. So potentially, but that's not the details of statistical mechanics are not covered in this class. Okay.
Sorry, we have a couple questions.
Okay.
Oh, sorry.
Go on.
People who've asked, why can you take the average between the two different thermal expansion coefficients here on the example 3?
Okay. Okay, so let's take it. Thanks, Janet. Let's take it one at a time. So here you can take the average, or I chose to take the average because I was given two values, and because the temperature range is quite large, I decided instead of using the linear coefficient of thermal expansion for one or the other, you can take the average, and it can be reported in that way. These values can be reported as averages over a range of temperature. Now, if you're not given two values, then of course you can't take the average, and you could see, which one is more accurate, right, as you do your experiment. But here I've taken the average so that I know what the linear coefficient is going to be over this wide range. Now, sometimes you do see in the literature that people will just report one value over the other, and that should be noted, or the paper will have noted that.
And I think there's one last question of, will they need to consider non-symmetrical crystal structures when doing their thermal expansion problems? Sorry.
Yeah, for the purposes of this class, no. And if you were given a material that's not face-centered cubic or body-centered cubic, that lacks symmetry, then of course most likely we will be discussing in a 1D case where it's perfectly fine to use the linear coefficient of thermal expansion, because we're just dealing with the expansion in that direction. So yeah, we wouldn't necessarily overcomplicate things. Okay, have we all caught up to with all the questions, Janet or Tony?
Yes.
So yeah.
Okay, great. Thanks a lot. So I'm just going to continue on, and then we'll pause after a little bit as the questions come up again. Okay. All right. So now here's another example where instead of increasing temperature, we decrease the temperature. So here's an example of a copper wire that's 15 meters long, and it's cooled from 40 degrees Celsius to -9 degrees Celsius. So how much change in length will this copper wire experience? And we have been given that for copper, the linear coefficient of thermal expansion is 16.5 times 10⁻⁶ ppm. And so once again, we need to know the relationship between the fractional expansion or compression and the temperature change, right? And so once again, we know that delta L over L naught being the original length, is related to the coefficient of thermal expansion times the change in temperature. And so this means then that delta L is just L naught times the linear coefficient of thermal expansion times the change in temperature. So here it says average, but clearly we're given only one value, so we're going to use that value, even though you're spanning 40 to -9C. Oh. And so we know that the change in length is going to be, we'll start at 15 meters, and the coefficient is and so the change is actually going to be and we should note that this is going to be shorter, right? So this should be expansion or contraction, right? So it's going from 15 meters to 0.12 meters shorter. Okay, so here, even though we're spanning this temperature, because we're given one value, we're just going to use it and not take the average. Or this may be the presumptive average that we're given already, but we're only given one value, and so we're going to use it. Okay, so now we're going to shift a little bit and talk about thermal conductivity, and that is the material's ability to transport heat. Right? And we have some intuition of this already. Some materials, get hotter much faster. So we're going to talk about, that rate, the heat flux. And so we're going to talk about Fourier's law, in which the heat flux is dependent on thermal conductivity and the temperature gradient. And so we can describe that heat flux as it is related to the thermal conductivity K times the change in temperature over the change in the length of that material. So here, once again, we're considering 1D. And so, oh, I think somebody caught a typo. Yeah, oh, yeah, sorry, thanks. Yeah, TF should be -9, thanks. Right, TL. Okay, so back to thermal conductivity. Right, so the heat flux that flows through a material is related to the thermal conductivity times the change in temperature, the temperature gradient. And so where you've seen this type of equation before is when we talked about diffusion and Fick's law, where the flux is related to the diffusivity times the concentration gradient. And so when we're talking about, thermal conductivity and what will inhibit or accelerate, the heat flow, we have to think about, what's actually happening at the atomic level. So what you have at the atomic level is that there are atomic vibrations, and so those are the phonons. And then there are also free electrons, right, in certain types of materials that can flow. And so they'll flow from the hotter regions to the cooler regions. And so the thermal conductivity consists of both the phonon, or the atomic vibrations, as well as the electronic component. For metals, the electronic component really dominates the heat flux, right? And so K sub E increases with increasing free electron concentration, because there are more electrons that are available to participate in the heat transference process. This is less so for the case of ceramics, right? There aren't as many free electrons, and so it's really dominated by atomic vibrations or phonons. But of course, that's not as big of a part as Ke. And so for thermal conductivity in metals, especially high purity metals, the electron mechanism of heat transport really dominates and is much more efficient than the phonon contribution for thermal conductivity. And thus, metals are good conductors because they have a large number of free electrons that participate in thermal conduction. And if you have high purity metals, you really don't have imperfections to scatter these electrons. So they're really good heat conductors. And so if you have, ultra high pure copper, it's a really good conductor for that reason. Now, if you have introduced, other elements into the system, you have substitutional atoms, you see here the thermal conductivity decreases as a function of increasing zinc in some other matrix of metal as you increase the composition and alloy the material more. And so there's a rule called the Wiedemann-Franz law that gives you the relationship between the electroconductivity, the thermal conductivity, and then temperature that it's at. And for these types of materials, it's mostly constant. It really hovers around this value, 2.44 times 10 to the negative 8. And so what you see reported in your book and elsewhere is that it really hovers around these numbers, maybe by a factor of 2, but the magnitude's going to be the same. And so if you have ultra high pure materials, it's going to conduct heat very well, very low impurity. But as you increase, let's say you're strengthening your material, so you'll maybe have solid solution or something like that. As you do a number of things to increase the strength of your material, like cold work or something like that, you're actually introducing defects that actually can be counterproductive to heat transport. So depending on what you want, if you're increasing strength or increasing, that could decrease your thermal conductivity. For ceramics, they generally have low thermal conductivity. Because once again, there isn't a whole lot of the free electrons that will dominate the thermal conductivity value, and thus what you have is phonon transport. And so here are some examples of ceramics and glasses where you see it's actually much lower. And so the value, some of these values will change, but we can assume that even if delta T is large, that these values will linearly change with temperature. So we can extrapolate some things for high temperature. We have some value for these materials for the low temperature thermal conductivity. For the thermal conductivity of polymers, here you see the two figures from previous modules where we have to think about the crystallinity of your polymer since heat is conducted through covalent bonds. And we know that there are carbon-carbon covalent bonds in the chains, but there's a secondary van der Waals bond that is much weaker in between the chains, right? And so if you just have, your regular semi-crystalline polymers you see here, it's somewhat isotropic. But as we discussed, with mechanical properties of polymers, that you really sometimes want to extrude them so that you get higher strength, and then the chains will start to align like that you see here. So even the amorphous regions, start to align. Your crystalline regions also align, as you see here. And so the heat conduction along these chains will be faster than, of course, in the transverse direction or in between the chains. And so here, we go back to that question that was posed, which is, will we have to deal with anisotropy? And so, yes, in this case, you would, but most of the time we would be talking about, the thermal conductivity in the direction of interest, which is in the high conductivity direction. And so higher crystalline polymers with higher crystallinity will conduct heat better than the more amorphous polymers. And of course, that now goes back to the crystal structure and the atomic bonding of your polymers, right? So if the polymer is isotactic, syndiotactic, or atactic, that has implications on the resulting thermal conductivity of that polymer. So here you see some examples of the thermal conductivity K for polyethylene, high density, polypropylene, polystyrene. So they're all pretty low relative to what you saw for metals. And what I was talking about just in the previous slide is that, yeah, if you have isotactic polymers, right, that means all the R groups, this is for polypropylene, all the R groups are on the same side of the chain, right? So we would draw that as, you know, let's say all the R groups are the same, on the same side like this, iso being the same. They would have the highest conductivity because these types of polymers will crystallize most readily, even though, you know, 100% crystallinity is impossible to achieve, but we can get some pretty high numbers, and thus isotactic polymers will have the highest conductivity. Syndiotactic, all right, it's alternating, so you can see here on either side, and so the conductivity will be somewhere in the middle. And then of course, if you just have random functional groups where it could be on either side randomly without some reasonable periodicity, then these types of polymers will have the lowest thermal conductivity because they're not going to crystallize as readily, okay? And so when we look at the structure of polymers and also the mechanical properties of polymers, we can now also dictate and predict the thermal conductivity of polymers just based on how, where we know the functional groups to be and how they pack. So this slide should have been with the ceramic slide, but you could see here, there is a change in thermal conductivity as a function of temperature. And so, you know, depending on where you are, you can see that graphite can actually have one value for, this must be in plane because it's higher than that of beryllium oxide, magnesium oxide, and alumina. Graphite is quite particular because, as you remember, there are layers, right, of graphite. And so if you exfoliate one layer, that's graphene. So thermal conductivity is much higher in the lateral direction than, of course, in the transverse direction in between the layers of graphene and graphite. Right? Similar to polymers, because there's van der Waals type bonding in between each of the layers for graphite. Okay. So let's go through some cases for the remainder of the time. So which material will have larger values of thermal conductivity? So here you have, you know, let's say pure copper versus a bronze where you have 95% weight copper and 5% weight aluminum. Well, if we think about impurities and how the free electrons will scatter, copper will have the larger value of thermal conductivity, because here the aluminum atoms in 95% weight copper will scatter these free electrons, and scattering will decrease thermal conductivity. Vitreous silica, so this is amorphous silica versus quartz, which is, you know, highly crystalline. Well, quartz will have higher thermal conductivity because the amorphousness of the silica will actually scatter your phonons or your lattice vibrations, and thus quartz will have higher thermal conductivity. So once again, we go back to crystallinity argument. Linear polyethylene versus branch polyethylene. So here, the linear polyethylene will have higher thermal conductivity because our argument goes back to crystallinity, right? Linear polyethylene chains can pack more readily, and thus they can, a linear polyethylene can have greater crystallinity than the branch polyethylene, which is more bulky and doesn't pack in as well. And the heat transfer is accomplished by these molecular vibrations, and so they'll coordinate better if you have higher crystallinity. And for, let's say you have the copolymers, random polystyrene butadiene, which is of course used a lot in the rubber industry, or alternating PV copolymer. Well, the alternating will have higher crystallinity, and thus the thermal conductivity will be higher than that of just, random or atactic copolymers, right? So with that, I think I'm 2 seconds over the class time. And so with that, I'll end the section or the lecture for today. All right. Have a good day, everybody.